Right, hello again grade 12s. Please note that this video goes hand in hand with a worksheet entitled Examples on Optimization Rates of Change in Calculus of Motion. This worksheet has been uploaded to the Google Classroom. So the whole idea here is that you first download the worksheet and then you try an example. So you go example by example. You first try and do it yourself, and then only after you've completed each one of these questions, you look at the video and you look at the way that it's supposed to be done, marking it, and then also hopefully understanding any issues you had while you are marking it. And then once you've gone through this question line, pause the video and then do the next example on your own. So the whole idea is literally do a question, play the video, this particular video, mark your question, pause the video, and then go back to the worksheet, do the next question in the worksheet, and then once you're complete, then play the video again and then watch the rest of it. So that's the way that's supposed to work. Please, like I said, try the examples yourself before you just go and look at how it's done. Right, so let's look at the first question on this particular worksheet. This particular question is from the Department of Basic Education, from their National Senior Certificate, February-March 2019, and it's question 9. So what they say in this particular question is they say, a piece of wire that is 6 meters long is cut into 2 pieces. One piece, which is x meters long, is bent to form the square ABCD. So this square right over here, if I highlight it, that is formed using that x meter long wire. Then the second piece of that wire is then bent into what they call a U shape, like this, and then it forms the rectangle BEFC if it's placed next to the square ABCD. So what you should realize is you should realize all together, if I go around like that and I go around like that, all of that is equal to the entire wire, which was 6 meters long. And then all around like that was equal to that one piece of wire that was cut off, which was specifically that x meters of wire over there. Okay. Now what they ask is they ask, calculate the value of x for which the sum of the areas enclosed by the wire will be a maximum. So you want to know the sum of the areas must in other words be a maximum. So first thing you need to obviously realize is you need to realize that if I add AB, BC, CD and AD all together, plus then BE, EF and CF, that's going to be my 6 meters. Whereas if I add these sides, AB, BC, CD and AD, that's going to be X. Now because this is a square and it was given that it was a square, these 4 sides must therefore be equal. And because it is attached to form a rectangle, it means those 2 sides must be equal, and it means these sides must be equal, specifically because the rectangle is attached to the square. So that's the very first important thing you need to realize. Then obviously, because the entire perimeter over there is equal to x meters, I can then go and I can say, but this is x over 4, this is x over 4, this is x over 4, and this one is x over 4. Because obviously we are bending it in such a way that it's forming a square where all 4 sides are equal, which means this side is then also equal to x over 4. Okay. Then what you need to realize is this pink stretch over there. So just that pink stretch, so BE plus EF plus CF, let's write that down. That is equal to the 6 meters of wire minus the x meters that were taken away to form that square over there. So you can then go and you can say, okay, but BE is then in other words equal to CF. So these two are equal to each other, and because they're equal to each other, you could then go and call them Y. And this one we've already seen is then equal to x over 4, so I'm going to write x over 4 there. And I can then go and I can write y in terms of x using this particular equation. Because I have spoken to you guys about these optimization problems before where I said you can't have 2 variables. You can't have an x variable and a y variable when you're trying to maximize. You can only have 1 variable. And that's why we want to write that y in terms of x. So obviously y plus y is then equal to 2y. And then this is going to be 6 minus x over 4, which is then going to be minus 1 minus a quarter, which is then minus 5x over 4, If you don't know how I got it, you can actually use your calculator, and you can simply go and you can say 1, so minus 1 over 4 is an equal to minus 5 over 4x. And then we need to divide everything by 2. So y is then going to be equal to 6 divided by 2, which is 3. And if you divide that one by 4, again, if you're not very good with fractions, you can use your calculator. That's going to be 5x over 8. Careful. A lot of you might have thought it's 5x over 2. It's 5x over 8. You can check. You can say that divided by 2, you'll see is minus 5 over 8. Good. Now the whole idea is you need to go and you look at what they ask for you to maximize. And what they specifically ask for you to maximize is the sum of the areas. So you want to maximize the sum of the areas. Therefore, we need to set up an equation that is going to represent these areas. So the first one is going to be the square. So the square is going to be x over 4 times x over 4, which is x over 4 squared, plus. The next one's going to be the rectangle. So the rectangle is supposed to be that x over 4 times y, but we have already gone and we've said I can write y in terms of x over there. So that's going to be the length of the square, of the rectangle, and that's going to be the width of the rectangle. So x over 4 times 3 minus 5x over 8. There you go. Okay. So obviously we need to simplify this first before we can go and we can find the derivative, because remember, whenever I'm trying to maximize, this is something you should immediately know. Maximization means take the first derivative and set it equal to 0. Okay, so first we're just going to do the algebra over here. So we're going to say that is x squared over 16, because you have to square the numerator and the denominator. Here we're going to distribute, so we're going to say that's 3x over 4 minus, and that one is going to be 5x squared over 4 times 8, which is 32. Now, you could actually go and you can find the derivative of that one, but I am quickly just going to add those two like terms, just to simplify it fully before I do go and find the derivative. And again, if you're not very good with your fractions, you can simply go and say that it's 1 over 16 minus 5 over 32. Which is going to give you minus 3 over 32. There we go. So I've now established the formula of the area, which is the sum of the areas of those two, and that is what I want to maximize. So again, I want to reiterate maximization, or if I have to minimize, then I'm always going to go and find the first derivative and set it equal to 0. So here we go. The first derivative of that particular function is going to then be equal to 3 over 4, because that's the coefficient of x. And remember, when I find the derivative of anything with x, all that remains is the coefficient, so that's 3 over 4. Now this one's slightly more tricky. You could move the x squared next to it, just so that you remember I have to take the exponent, which is 2, multiplied by the coefficient, which is minus 3 over 32. So it's that minus 3 over 32 times 2, which is going to be minus 3 over 16. And then obviously I'm going to take 1 away from the exponent, which means take 1 away from 2, and that's going to be minus 3 over 16x. Great. So that is then my first derivative. And like I said, I have to show that I'm setting it equal to 0, otherwise they're going to penalize me. So we set that first derivative equal to 0. Otherwise you won't have an equation to solve. Then I'm going to say 3 over 16x is equal to 3 over 4, and I'm going to divide both sides by 3 over 16. So I'm going to say 3 over 4, 3/4, divided by 3 over 16. And that's going to give me 4. So now I've got an answer, and you have to be very careful once you've gotten an answer that you then go and read the question to make sure that you've finalize the question, so that you don't go and you miss out on the last couple of marks that you can potentially get. So the question again said, calculate the value of x for which the sum of the areas enclosed by the wire will be a maximum. And that's it, we've calculated x. They could have gone and they could have said, instead of saying calculate the value of x for which we have a maximum area, they could have asked me what is the maximum area. So they asked you what is the maximum area. You would have had to go back to this formula we established for area and substitute x in there and substitute x in there, and that would have given you the maximum area. But because they didn't ask you for the maximum area, they just asked for the value of x, we're done, finished, and we can stop. That is the final answer. Right, welcome back. This is the next question in the worksheet, question 12, which is from the Department of Basic Education, National Senior Certificate, November 2009. Now in this particular question, they give you the following formula, and they say a tourist travels in a car over a mountainous pass during this trip. The height above sea level of the car after T is given by this particular formula, which is the height above sea level in meters, and the journey lasts exactly 8 minutes. So they've given you a formula to work with, and you're going to work with that formula. Unlike the optimization problems, you don't have to go and create the formula, you just have to work with whatever formula they give you. So, first question, 12.1. They asked, how high is the car above sea level when it starts its journey on the mountainous pass? Now, this pretty much refers to my initial height above sea level, and we have spoken about this when I spoke to you guys about calculus of motion, where we talk about instantaneous displacement and instantaneous velocity. Sorry, not instantaneous, I should rather say initial velocity and initial displacement. That's actually more the term. So the whole idea is here, before anything happens, what was then specifically the height above the sea level, and you can also even talk about what was the initial velocity. But the point is, initial always refers to when t is equal to 0. So very important, when you ask how high was the car above sea level when the journey started, or in this case, what was the initial height above sea level, it's where t is equal to 0. And because they ask for the height above sea level, we're going to use this formula. Be very careful with the formulas. This formula specifically will always refer to height above sea level. If I want to go and I want to work out the rate of change, or I want to work out the velocity, then only will you go and you will find the first derivative. So don't just automatically go and find the first derivative and think that is what you're supposed to use. Not in this case. In this case, they just asked what is the height above sea level. So I'm simply going to substitute the 0 into that formula. So the S of 0. Quite easy, because obviously every single time I put 0 in there, 0 in there, 0 in there, it's equal to 0. So all that's remaining is that 100. So it's 100 meters, because they told me it's height above sea level in meters. Sorry about that. Okay, so that means my height above sea level right at the beginning is 100 meters. 12.2. Okay, now 12.2 then asks, calculate the car's rate of change of height above sea level with respect to time 4 minutes after on the mountainous pass. Now the following words, car's rate of change. We've spoken about rate of change. Rate of change is always my first derivative. So when they ask for rate of change, without even thinking about it, you have to find the first derivative of whatever formula they've given you. So in this case, first derivative of that formula, which means 3 times 5 is then 15t squared, minus 2 times 65, which is then going to be 130t, plus 200, and then obviously the derivative of a constant is equal to 0. So that right there is my first derivative, which is then also my rate of change. But they specifically want to know the rate of change after 4 minutes, so I'm going to substitute 4 there into t. So 15 times 4 squared minus 130 times 4 plus 200. And I'm going to be lazy and grab my calculator. And that's going to give me minus 80 meters per second. Because when you do rate of change, you always have to remember rate of change is going to be the one variable, specifically the dependent variable with regard to the independent variable. That's your delta y over delta x. So that's why y is the height above sea level, that's why it's meters, and then your time is going to be, oh sorry, got that one wrong. Apologize profusely, because the time is in minutes, so that's meter per minutes, because they did tell me at the beginning this is going to be in minutes. But the whole idea here is very simple and straightforward. My units is going to be whatever the units is of the y value, the dependent variable, over whatever the units are of the x value, the independent variable. Okay, right, so that is going to be minus 80 meters per minute. Now, the next one then is 12.3, and in 12.3 they ask a very interesting question. They say, interpret your answer to question 12.2. Now, that interpretation specifically refers to the minus over there. And the reason it refers to the minus over there is because 80 in itself is not really all of that interesting. But we've spoken it before with calculus of motion specifically, where we said you can actually have negative velocities in this case. Or you can also have, in this case, a negative rate of change. So that negative rate of change specifically refers to the fact that it is decreasing. So in this case, we're going to say the height above sea level is decreasing by 80 meters per minute after 4 minutes. So it's just referring to the fact that because it's negative, it's a negative rate of change. Remember, I spoke to you guys about the fact that negative rates of change is also referred to as negative gradients, because the rate of change and the gradient is the same thing. So a negative rate of change is a negative gradient, and we know gradient refers to the fact that it's decreasing. So the height above sea level is decreasing by 80 meters per minute after 4 minutes. That's pretty much the interpretation. Okay. Then 12.4, they ask, how many minutes after the journey has started will the rate of change of height with respect to time be a minimum? So they're saying, how many minutes after the journey has started will the rate of change of height with respect to time be a minimum? Now, this is a horrible question just because of the language. And the reason I say it's a horrible question because of the language is normally the way they would ask this question is they wouldn't ask where will the rate of change be a minimum. They will say where will the height above sea level be at a minimum. Now, if they go and ask where will the height above sea level be a minimum, then you would have had to go and find the first derivative of this and set it equal to 0 to know what the height above sea level. But that's not what they asked. They asked, after how many minutes will the rate of change be at a minimum? So that means that it's got to be where the rate of change is a minimum. So we first have to find the derivative of the rate of change and set that equal to 0. So hopefully you guys are understanding why we now have to go and not set the first derivative equal to 0. We have to actually go and set the second derivative equal to 0 to know where the derivative is at a minimum. So very, very important concept. Where the original function is at a minimum is where the first derivative is equal to 0. But where the rate of change is at a minimum is actually where the second derivative is equal to 0. So it's all about the language here. So we first have to go and we have to find that second derivative. And we'll just do it from here, there. And we'll say that's 2 times 15, which is 30t, minus 130. And then obviously that's a constant, so it falls away. And that's what I'm going to set equal to 0. Because I don't want to know where the height above sea level is at a minimum. I want to know where the rate of change is at a minimum. So that's why I have to set the second derivative equal to 0. So that's where 130 is equal to 30t. So I can divide that 130 by 30, which is going to give me 4,3 if I round it off to 1 decimal place. Keep on doing the seconds, but it's minutes. So after 4,3 minutes, the rate of change is at a minimum. So yes, I can understand that you guys might have gotten a little bit confused, especially if you tried this on your own. You might have just read the word minimum, and because I've said to you guys so often that minimum or maximum is where we set the first derivative equal to 0. A lot of you would have then set the first derivative equal to 0. But they were tricking you guys by not asking where the height is at a minimum. which would have been the first derivative, equal to 0, they were tricking you by asking you where the rate of change is at a minimum. So hopefully you understand that if I want to get the rate of change as minimum, I had to set the second derivative equal to 0. Okay, here's the next question in this worksheet. So this question comes from the Department of Basic Education in the National Senior Certificate for November 2011, and it's question 11. So in question 11 it says, water is flowing into a tank at a rate of 5 liters per minute. So you've got that rate of 5 liters per minute that the water is flowing into the tank. At the same time, water flows out of the tank, so the water flows out of the tank at k liters per minute. The volume in liters of water in the tank at time t, so the volume in liters at time t, is given by the formula Vt is equal to 100 minus 40. Now the first question, 11.1, says, what is the initial volume of water in the tank? And I've spoken to you about this word initial before. Initial is where t is equal to 0. And specifically, they're asking, what is the initial volume? So we're not going to find a derivative here. We're just going to use this formula because this formula gives me volume. Be very careful about what formula it is that you're using. I've said this before. Are they asking for initial rate of change? Then you have to sub 0 into your first derivative. Or are they asking for the initial, in this case, volume? And this formula gives you volume. So that's where you have to substitute it into the formula without making any changes. So we say the initial volume is going to be where t is 0. And that's quite simple and straightforward, because if I multiply there by 0, it's going to be 0, which means I just have 100, and this, as they said, is measured in liters. So that's going to be 100 liters is the initial volume in the tank, and that's why it only counted 1 mark. Now 11.2 then, they ask, write down 2 different expressions for the rate of change of the volume of water in the tank. Now, the reason they want you to write down 2 different expressions simply has to do with they've given you 2 pieces of information. The first piece of information just says water flows into the tank at 5 liters per minute and it flows out of the tank at k liters per minute. And then we've got this one which indicates volume. You could actually start with this one. And the reason you could start that one is hopefully by now you guys know that rate of change is always going to be my first derivative. So if I do the first derivative of that formula, right there, I can then go and I can say, oh, that's just going to be equal to minus 4. Because the derivative of a constant is 0, and then the derivative of that minus 4t is just minus 4. So that's the first expression you can use. The second expression you can use is you can also call it v cent of t, or the first derivative of t if you want to, is you could have just used the information they gave you over here. And the information they gave you over here was they said water flows in at 5 liters per minute, it flows out at k liters per minute. So obviously that is an increase of 5, that is a decrease of k. So if it's flowing in at 5 and it's flowing out at k liters per minute, the difference between the two is then going to be my rate of change. And that is why 11.3 then asks you, determine the value of k, that is the rate at which the water flows out of the tank. So what you can do now is you can say, oh, but this means that I've got -4 as my rate of change, and then I've got this one also as my rate of change, so I can just set them equal to each other. Which means k is then going to be equal to 5 plus 4, which is 9. Now, you need to understand in the context of this problem, that means the water flows out at 9 liters per minute. And I know a lot of you would have expected it to be negative, but it also has to do with the fact that over there, when I set it up, I said it's minus k, and because I put the minus there, that's why this one turned out to be positive, because it's flowing in at 5 liters per minute, it's flowing out at 9 liters per minute, which gives me a difference of 4, and specifically a decrease of 4 overall. And that's what they asked, determine the value of k, the rate at which the water flows out of the tank. So it actually is a very, very simple, straightforward question, unless you complicate it. Right, so that's the end of this question.